So if I go to the graph and I label on the graph, I have 1, 2, 1, 1, 2 as a maximum. Maximums look like this. I have a minimum at 2, 1. 1, 2, 1. That's a minimum. Okay. Not only that, I could find intercepts and other things. That's really for section 3.5. For now, I want to apply the second derivative test. If I take the second derivative would be 12x minus 18. I want to know where that equals 0. Kind of like what we did right there. Take a 6 out. That would be 2x minus 3 equals 0. I'm getting x equal 3 halves. There's 3 halves. There's the second derivative. And again, my entire conclusion is based on f, always. I want to know a point to the left of 3 halves, say 0. If I put a 0 there, 0 minus 18 is negative. We said if the second derivative is negative, the graph is concaving down. And if I pick a point to the right, say 2, if I put 2 there, 24 minus 18 is positive. So we do know that f is concaving down from negative infinity to 3 halves, and f is concaving up from 3 halves to infinity. What that means, we do have an inflection point because we switched from concaving up to down or down to up at 3 halves, and if I plug that in right there, I will get 3 halves. I did that on my calculator. So the point 1.5 is an inflection point. Now concaving down, if you really want to kind of get concaving down, remember it's like a parabola, something like just sketching a rough graph. I could do a better job than that. We just want to tackle this idea for now, and that's concaving up. And the graph looks something like this. Alright? Number 12 is next. Same directions. Well, if I take a derivative of the top times the bottom, minus the top times derivative of the denominator, all over the denominator squared, f prime will equal x squared plus 1 minus 2x squared. So 1 minus x squared over x squared plus 1 squared. So I need to know where does the derivative equal 0, where does the derivative not exist since there is a fraction. Well, this is nowhere because the denominator cannot equal 0, but a fraction equals 0 if the top equals 0, and that means x equal plus or minus 1. So the testing here is going to happen at 1 and negative 1. There's x equal 1 and there's x equal negative 1. There's the derivative, there's f. If I pick a test point to the left of negative 1, let's say at negative 2, do you agree that the denominator is always positive? If I throw a negative 2 in there, 1 minus 4 is negative. A number between negative and a positive, 0. If I throw 0 in there, the top will be 1. The denominator is always positive. And if I pick, say, 2, 1 minus 4, that's negative. We know if the derivative is negative, the function is decreasing. Derivative is positive, is increasing, then decreasing. And we want to say that f is increasing from negative 1 to 1. F is decreasing from negative infinity to negative 1, union with 1 to infinity. We have a local minimum at x equal negative 1. F is increasing, F is decreasing, and F holds a local max at x equal 1. And I could go to the function itself. If I put a 1 in there, I'll get 1 half, negative 1, negative 1 half. So 1, negative 1, negative 1 half, and 1, 1 half. I'm going to put those on a grid. It's not asking for a graph yet. That's what section 3.5 is. It asks for all of these plus the graph. Here we're going to do a rough sketch. We're not finding the intercepts or anything like that. We know we have a minimum at negative 1, negative 1 half. At negative 1, negative 1 half, minimums look like this. And we have a maximum at 1, 1 half. We know what that graph looks like, right? We know that this has horizontal asymptote y equals 0. Either the graph looks like this or like this. Since I got this on the bottom, it looks like that, so it looks like the graph is going to look something like this. I got the minimum value and I got the maximum value. Now for the second derivative, well, this is no fun, but well, it depends who you ask, right? The second derivative, the derivative of the top is negative 2x times excuse me, the denominator, and this is something you guys were asking about, minus the top. Derivative of the denominator is 2 into x squared plus 1 times 2x all over the bottom squared. You're wondering, what were you asking about? You were asking me how to factor that when we did a derivative back in the days. And I said in the next chapter you're going to have to do that. Well, I need to factor the top. What's the common factor? I'm going to take out negative 2x, negative 2x, and I'm going to take one of those. Out of the first, I'll have x squared plus 1. The minus I took out, there's a plus, and the only thing left is this product. 2 into 1 minus x. To the top times the bottom minus the top times the bottom. That is a 2. So I'm just doing that for you. Notes x squared plus 1 plus 2 minus 2x squared over x squared plus 1 to the 4th. The second derivative is 3 minus x squared over x squared plus 1 to the 4th. Now, where does the second derivative equal 0? Where does the second derivative not exist? Well, this is not going to happen anywhere because the denominator can equal 0. The top will equal 0 when x equals plus or minus radical 3. And the same test one more time as we just did. F double prime f. I have a radical 3. I have a negative radical 3. I pick a point to the left of negative radical 3. The denominator is always positive. If I pick negative 4, 3 minus 16 is negative. So negative over a positive is a negative. If I pick 0 and I put that in there, that's positive and a negative. If it's negative, it's concaving down. If it's positive, it's concaving up. And if it's negative, it's concaving down. And f, right underneath it, it seems, f is concaving up from negative radical 3 to radical 3. And it's concaving down from negative infinity to negative radical 3 union with radical 3 to infinity. And we have an inflection point, 2 of them. One at negative radical 3, and if I plug that into the original negative radical 3 over 4, and radical 3 over 4, those will be my inflection points, and let me show you how that looks on the graph. So if I go by negative 1 point sum, oh, I should use a different color. Let's use this. That's an inflection point. And radical 3 is 1 point sum. That's an inflection point. So basically what you're picturing, a parabola opening downwards. Oops. Let's go back. Let me do it slightly different. There we go. So it says, and let me follow up. Let me use different colors. Here we go. It says f is concaving down. Concaving down. Well, I know that's an asymptote. So isn't this concaving down to this point? Instead of that continuing down, it's gonna pick up on something that's picking up, and it's right there. So this is concaving up. Something's not adding up. Something's not adding up. Let me check. What is that? Huh. Give me a sec. Let me check what one. Okay, guys. We did say we're factoring out. Do you remember what we said we're factoring out? We said we're factoring out of the top, the yellow part. We're factoring out the negative 2x. So there's a negative 2x multiplied. Do you remember that? Oh boy. Okay, you know what? Yeah, I can fix it. So we said we're going to factor out this yellow part. I'm going to redo the problem. That takes forever. We're going to take out negative 2x we're going to take negative 2x into x squared plus 1. We're going to take out a negative 2x into x squared plus 1. So when we get this far, there's a 2x, and that will make that a 3. Because this will cancel with one of those. So, in addition to what I have, perfect, see? You shouldn't always take. So where does it equal 0? It also equals 0 at 0. 0 is another inflection point. If I pick negative 1 and I test it right there, that's a negative, and that's a positive, so that's a, let me check. If I put a negative 1, 3 minus 1 is positive, positive times a negative, okay. If I put a negative 1, I should have left it on the other side, my mistake. So this is what happened when you try to fix things. That's negative 2 there. Well, if I put a negative 1 there, negative times a negative, that's positive times a positive, that will be a positive. Right? So that's, and if I put 1, negative 2 times 1 is positive times a negative is a negative. Now I feel much better. We have another inflection point at 0, 0. Wow. See, the graph wasn't adding up. Something was wrong. So, we have concaving down. Very good. Now it's going to concave up to 0. So instead of continuing down, this part is going to pick up. And concaving up looks like this. And it should continue on, and that's a minimum. But then we have concaving down again from 0 to this point, right? The other inflection point. And then, instead of continuing down, it's going to pick up, and we have concaving up from this point all the way to infinity. This is an inflection point. This is an inflection point, and this is an inflection point. If you really want to see it, this is coming down. This is coming up. This is coming down again. And this is looking like a parabola, so to speak. There it is. Pretty cool, huh? Don't you think? Now, something I want to mention. And there's the homework. 1 through 13 odd. On number 16, you're going to ignore directions and use the same directions as number 9 through 14. Basically the same as what we just did. And do number 45.